In 2017, a malware called WannaCry infected hundreds of thousands of computers and medical devices in 150 different countries in a few days. WannaCry utilized code likely stolen from the United States' National Security Agency called Eternal Blue to exploit Windows services, and it spread itself like a plague. WannaCry then encrypted the victim's machine and demanded payment from its owner. WannaCry was ultimately defeated using reverse engineering techniques and the analysis of assembly code to identify a kill switch. This was probably invented by Dr. Doofenshmirtz, who called it the Ransominator. Assembly language gives us a powerful way of analyzing malware, but it can be difficult to understand for the untrained. In this video, I will give you the power to utilize this amazing tool. On March 14th, 2017, Microsoft released a patch for a new server message block, or SMB, vulnerability. Microsoft Windows uses SMB to share files among computers on the network. The vulnerability was related to 3 bugs in Windows implementation of SMB. The first bug was a mathematical error when calculating memory allocation. The second was a buffer overflow enabled by the first. The last bug allowed heap spraying where the attacker could write executable code. On April 14th, a hacker group known as the Shadow Brokers, possibly a reference to Mass Effect's Shadow Broker, released what they claimed to be a list of hacking tools curated by the NSA. Hold on, just let me finish this last mission! One of these tools was called Eternal Blue, which exploits the SMB vulnerability previously patched by Microsoft to install a backdoor called Double Pulsar. However, because of slow patching, many Windows machines were and still are vulnerable to Eternal Blue. Nearly 1 month later, on May 12, 2017, WannaCry was released to the world. WannaCry is a dropper, a program that extracts other programs within it, with 3 components. First, an encryptor and decryptor that encrypts many of the files on the machine. Second, a message application to instruct the user on how to get their files back by purchasing bitcoins for the attacker. And 3, Eternal Blue to spread itself to other computers internally and externally to the network. WannaCry is suspected to have come from North Korea and infected 200,000 computers within days. One of the biggest organizations hit was the National Health Services in the UK. They had 70,000 devices infected, including MRI scanners and blood storage fridges. While the ransoms did not cause a lot of monetary payments, some security researchers estimate damages were in the billions of dollars. Security researchers embraced the challenge to stop WannaCry. On March 13th, the security researcher Marcus Hutchins, later to write malware himself, noticed that the malware always called out to a specific URL of an unregistered domain. Marcus purchased the domain, and the malware went into safe mode and reduced its infectious behavior. The technique of checking for a specific URL can have 2 purposes. First, it can act as a kill switch to stop it from attacking the attacker's own machines. And second, it can help hide the malware when it thinks it's being investigated in a sandbox. This URL is visible in the assembly code of WannaCry. Thus, in order to save the day like Marcus, it helps to speak assembly. After a programmer writes a program in English, a language humans can understand, the program needs to be compiled to machine code, a language computers can understand. Just like you can show your dog the alphabet, and your dog can recognize your scent, but neither can do what the other can do. A dissembler debugger is our translator from machine code to a human-readable format. You can read that, right? Don't worry, I'll get you through it. To start, you need to understand that your computer has a set of registers. Registers store data just like RAM, but less of it. In the x86 architecture, don't worry about what that is, just know that there are different types. There are 8 general-purpose registers called EAX, EBX, ECX, EDX, ESP, EBP, ESI, and EDI. Don't worry about what they stand for, just know that there's a bunch of them. In assembly, we can represent the transfer of data from one register to another with the keyword move. We can represent the movement of data in EBX to EAX like this. Move EAX, EBX. We can also represent the assignment of a register to new data using the same keyword. Thus, move EBX, 10 represents putting the number 10 into the EBX register. We can also move data stored in memory into a register. All memory locations look something like this. This is a hexadecimal value where the numbers are represented by 0 through 9 plus A, B, C, D, E, and F to represent 16 total digits. To put the data stored in memory into the register, we would use move EAX, and then the memory location. The brackets just mean we are referring to a memory location as opposed to the number itself. You can also move data from a register to a memory like so. In computer architecture, there are ways of describing the size of data. 1 byte is obviously a byte. 2 bytes is a word. 4 bytes is a D word. Sounds kind of like a dirty word, but it just means double word. And Q word, which is a quad word. If we want to move a D word into a register, we could use move EAX, D word, PTR, and the memory location stored in EBX. Meaning move the D word size data from the memory location stored in EBX to EAX. You can also refer to memory locations compared to other memory locations. For example, move EAX, brackets EBX plus 4 means move the data in the memory location stored in EBX plus 4 to EAX. In this example, if the memory location is 010F000, the new memory location is 010F004. You can also add or subtract hex values by using something like this. Move EAX, brackets EBX minus 10H, meaning subtract 16 from the memory location. Now for your first challenge. What is the value of the data in the memory location EBP minus 8? Pause the video and see if you can figure it out. Hopefully you came up with the number 1. Now, if you were to reverse engineer the C code for this assembly code, what would it look like? Pause the video and see if you can make a guess. Welcome back. If we replace the memory location with the variables A and B, we get something that looks like this. This says assign the variable A to 1, put the value of A into register EAX, then assign the variable B to the value in EAX. Since registers are meant for temporary storage of data, our code would not need to reflect that temporary storage. So our code would end up looking something like this. Note that the definition of int A and int B allocates the memory location that are referred to by brackets EBP minus 4 and brackets EBP minus 8. We know that they are ints because the number 1 is an integer, float, or pointer, and floats are not stored in general purpose registers. I know I didn't tell you that. I cheated a little bit. And 1 is too small to be a pointer, so it has to be int. Notice if you don't understand the code above, you'll need a small course in C programming language. It's only going to get worse from here. Now you can play the Tower of Hanoi game in assembly. Go ahead, I dare you. Now, isn't there more to life than moving things? Well, yes. You can add, subtract, multiply, and divide. Wait, Professor Gibney, I already passed kindergarten. Oh, is it nap time? Hold on. Yeah. Where was I? Oh yeah, arithmetic. Besides arithmetic, you can also do bitwise operations of not, flipping all the bits, and, or, and XOR, shift left, shift right, rotate left, and rotate right. Now is where it gets fun, and we get to jump through space. There are multiple jump commands that move us to a new memory location to continue running code. Jump commands are useful for if statements and are often preceded by a compare command, CMP. CMP compares two registers or a register and a value such as CMP EAX, 7. We can then use one of the many jump commands, depending on the logic of the program, like these. Let's take an if else statement and convert it to assembly. The first jump we want to make is when x does not equal 0. When x does not equal 0, we move on to the other code. So we're going to compare to see if x equals 0 and then jump if x does not equal 0. If we do not jump, we will assign x to 5. Then we need to tell the code to skip the rest by jumping to the end like this. In the else, if we need to compare to see if x equals 1 and jump to the else if it is not. Remember that JNZ is an alias for JNE, or jump if not equal. If we don't jump, we need to assign x to 6, then jump to the end. Finally, we need to do the last part if the other conditions are not met. Else, moved dword PTR to the memory location in EBP-4 and set that to 7. Normally, we don't use the words else if and else, but we replace them with the memory locations like this. Now for your next challenge. Reverse engineer this code. Pause the video and see if you can figure it out. Great, you're back. Hopefully you were able to figure it out. First, we can replace the memory locations with variables. Then we need to figure out what kind of conditional statement is here. If else, or if else. Say that 3 times fast.
If else, if else. If else, if else. If else, if else.
Since there is only one jump, it can't be an if else. This follows the structure of an if else, since there are 3 locations, and the last location just being the end of the program. Thus, we can replace the location names with the conditional structure, like this. Remember that the conditions are often reversed from the original C code. If we were to try to write this assembly in partial C, it would look like this. Now we can remove the temporary registers and finalize our C code. So if you feel like a superhero already, you can jump to the end of the video. Yeah, that was terrible. Okay. But the alternative is to watch the video in a loop. Speaking of loops, if you take a loop in C code like this, interestingly, both of these will produce the same assembly code. Here's the loop challenge. Pause the video and see if you can reverse engineer the assembly code. Hopefully you got something like this. Now that you've gone loopy, let's talk about pancakes. Computers love pancakes. See? Really? It's a thing. Check it out on Amazon. Just like a stack of pancakes, the last pancake you put onto the stack is the first one you eat. The stack stores variables that you can push on top or pop off the top. You can see this in the assembly code like this. Push 4, push 5, pop EBX. This is putting the top value into EBX. The stack is commonly used when calling functions. For example, this C function translates to this assembly. Notice that we call functions. The first lines are setting up the stack for the local variables. Then we can see arg0 being moved to var4 and arg4 being moved to var8. The args and var are referring to positions in the stack. This is just a small taste of assembly language, but it should get you ready to start working with a decompiler disassembler, which we are going to start getting into next week. If you like the content from this video, go read Learning Malware Analysis, as it is a great resource for this video. Watch for next week's video on the use of IDA to help reverse engineer malware.